Section 1.3 Continuity. In this example, we want to apply the intermediate value theorem. If you recall in pre-calculus, sometimes we need to solve an equation involving x. So we know how to solve quadratic equation or higher power polynomial that we can factor, we know how to solve. But sometimes we encounter situations such as the one in example 3, where this polynomial x cubed plus x squared minus x minus 2 cannot be factored. So how do we solve for such a equation? So this polynomial equals 0, how do we solve it? We will use numerical method, which is not going to be discussed in our Calculus 1 course. But the intermediate value theorem from calculus guarantee that such a method can exist. So how do we understand the intermediate value theorem? Let's take a look at the statement. Let f be a function that is continuous on the closed interval ab. So first we need continuity. And we want f of a not equals f of b. So the endpoint, the function at those endpoints cannot agree. If n is any number between f of a and f of b, so we need n to be between f of a and f of b, then there exists the number c in the open interval ab such that f of c equals capital N. So let's try to understand the theorem using a graph. We have the closed interval ab right here on the x-axis. We have f of a right here. F of e must be different from f of a, so we can choose randomly this area, okay, this point. So f of a is here, f of b is there. There's a difference. So if we have a point n on the y-axis, capital N, that is in between f of a and f of b, the intermediate value theorem guarantees that there's a value c in the interval ab that evaluates to n. So what it means? Well, because a function must be continuous, we have to draw a curve from f of a to f of b without lifting our pen. So you can look any way you want. Right, just an example. So this is a continuous function on AB that satisfies condition 1 and condition 2. Now we have 3 and in between f of a and f of b. We can see from the graph, okay, there is a correspondent to this point C such that f of c equals n. So how do we use the intermediate value theorem in example number 3 to show that this polynomial has a 0, meaning f of c equals 0 at some point c on the interval 1, 2. The first thing we need to verify is continuity. Okay, f of x is continuous. And it is continuous because we have a polynomial. So we do have continuity. Now second, we need to verify f of a, in this case is 1, is not the same as f of b, which is 2. So a is 1, b is 2 in this case. So we plug in 1 cubed plus 1 squared minus 1 minus 2 is negative 1. 2 cubed plus 2 squared minus 2 is 8. So we do have f of a not equals f of b. So then we want to see, is the value capital N that we're interested in between f of a and f of b? So 0 is our N. And 0 is between -1 to 8. Okay, so we have -1 is less than 0, less than 8. So 0 is between that. So the intermediate value theorem tells us that there exists a C in the interval 1, 2, so AB, such that f of C equals N. So that is the end of the proof. We just need to show that it's a 0. We don't need to find the 0. And in fact, the 0, C, the number C, is pretty complicated.